Welcome everybody. Today we'll be looking at an interesting graph theory question. In fact, we'll be looking at two graph theory questions that are closely related to each other. The first question is as follows. Let G be a graph with n vertices. For the purposes of this video, we'll only consider simple graphs where there are no loops and no multi-edges. Now, if G is triangle free, what is the maximum number of edges that G can have? I'll give you 5 seconds to pause the video if you would like to figure this out on your own first. Okay, so here is the solution for question 1. The claim is that firstly, m, the number of edges, equals to the floor of n squared over 4 is achievable. And for this, we can consider a complete bipartite graph, where on one side we have the ceiling of n over 2 number of vertices, and on the other side we have the floor of n over 2 number of vertices. I'll leave it as an exercise to check that this achieves the number of edges as claimed. Now the harder part of the solution is to show that m is at most the floor of n squared over 4. To do this, let G be a triangle free graph. B is the vertex set and E is the edge set. First, I claim that if xy is an edge, then the sum of the degree of x and the degree of y is at most n. Why is this the case? Well, if there's no triangle in G, then the fact that xy is an edge means that x and y cannot have any common neighbors. So the neighbor set of x and neighbor set of y are disjoint. The degree of x is this neighbor set, and y, the degree of y is the size of this neighbor set plus 1 for x. And the total number of vertices in this diagram here is at most the number of vertices of G. So the degree sum is at most n. So summing over every single edge exactly once, we have mn is greater than or equal to this sum over here. And we have this equality over here, which I'll explain. So for each vertex of V, we notice that it will appear in this summand here exactly its degree number of times. So we have the degree number of times multiplied by its value, which is the degree of V, gives us this sum over here. And multiply n on both sides of the equation to get this expression over here. And now we apply Cauchy-Schwarz inequality, where this is summation ai squared, this is summation bi squared, and we get summation ai bi quantity squared. And by the handshaking lemma, the sum of the degree of all the vertices is twice the number of edges, 2m. So squaring that, we get 4m squared. So rearranging the equation here, we see that m is at most n squared over 4. And since m is an integer, m is at most the floor of n squared over 4. So hopefully that's an interesting problem, but here is one that is even more interesting. Prove that every n vertex graph with at least floor of n squared over 4 plus 1 edges has at least floor of n over 2 triangles. So this is a very interesting phenomenon. Earlier we saw that with only floor of n squared over 4 edges, it's possible to get 0 triangles. But add one additional edge and all of a sudden the smallest number of possible triangles is the floor of n over 2. That is quite a lot of triangles. So this phenomenon is called supersaturation, and the inspiration for this name comes from chemistry. So here's the question we'd like to prove, and we'll prove it by induction on n. For cases n less than or equal to 4, I'll leave it to the viewer to check in directly. And the idea behind the inductive step is we try and find a vertex with a small degree, remove that vertex and all the edges incident to it, then the resulting graph will have one less vertex but still a lot of edges, and hopefully it meets the induction hypothesis, and that gives us a lot of triangles which we can use for the original graph. So this is the basic idea. but there are some subtleties which we will see now. So we actually need to consider two cases. First, suppose that the n we are proving now is odd, and all smaller values of n has been proven. Now m we are given that is the floor of n squared over 4 plus 1. I substitute in this value of n in terms of k. I get m equals to this expression over here. Now I claim that there is a vertex with degree at most at less than or equal to k. And this is because otherwise the number of edges is half of this is the number of vertices times the minimum degree of each vertices. So the number of vertices times the minimum degree of each vertices, and I half that because each edge is counted twice in this manner. So then I'll end up with this expression over here. And since m is equal to this, we cannot have m larger than or equal to this. This is a contradiction. So there must be some vertex with degree at most k. So what happens if we consider the graph obtained by removing that vertex and all edges incident to it? Now the number of vertices for the new graph is now 2k, and the number of edges is at least k squared plus 1 because we remove only at most k edges. And we check that this expression is exactly equal to floor of n prime squared over 4 plus 1. So we can use the induction hypothesis to conclude that G prime has at least k triangles, and these k triangles are all present in the original graph. And we need to show that the original graph has at least k triangles, right? So we are done for this case. And now for the other case, suppose that n is equal to 2k at even number for the n we are currently proving, and all smaller values of n have been proven. And in this case, substituting in this expression gives the number of edges to be k squared plus 1. Actually, we need to consider a further subcase. So again, we try and see if there are any vertex with a small degree. So in case 1, we just assume that this is the case. Assume that there is a vertex v such that its degree is at most k minus 1. Similar to what we saw earlier, we consider the graph G prime obtained by removing the vertex and all edges incident to it. And now the n prime is 2k minus 1. The number of edges is over here, and we remove at most k minus 1 edges, so we end up with n prime is at least this. And we check that this expression is equal to n prime squared over 4 float plus 2. So we can apply the induction hypothesis because this is obviously greater than the floor expression plus 1, right? So we conclude that G prime has at least k minus 1 triangles. But this is not quite enough because we needed to show that there are at least k triangles. So we are one triangle short. But notice that we have a slack here. So how do we use that? Well, we let E be any edge that belongs to a triangle in G prime. And now we actually consider G prime minus the edge. And this has the floor of n prime squared over 4 plus 1 edges. We apply the induction hypothesis to this graph actually, G prime minus E, to conclude that there are at least k minus 1 triangles. And this excludes the triangle that got destroyed when we remove E. So when we add E back, G prime has at least k triangles. And these k triangles are also present in the original graph. Okay, so this is the easier case where we have a vertex with a small enough degree to remove. As for the other case, we have to do something slightly different. So now we have all vertices having degrees at least k. We'll prove this by contradiction, so assume that there are at most k minus 1 triangles. Firstly, I claim that there exists an edge that does not belong to any triangle. To do this, we suppose otherwise and get a contradiction. So firstly, we have the number of triangles is at most k minus 1. So we have this expression here. Now 3 times the number of triangles can be seen as us looking at each triangle, and for each edge of the triangle, we add 1 to the total score. And therefore this 3 times number of triangles is the same as us looking at the edges individually and then summing up the number of triangles that each edge belongs to. And if we assume opposite to the claim, then the number of triangles that each edge belongs to is at least 1, and the number of edges is at least is k squared plus 1, so this sum is at least k squared plus 1. So we have 3k minus 1 is at least k squared plus 1. Rearranging, we get this quadratic expression over here, which we can show to be blatantly false, for example by completing the square. So since the claim is proven, I can just replace it with the statement that suppose xy is an edge that belongs to no triangles. Now just as before, we argued that therefore the neighbor set of x and the neighbor set of y are disjoint. Now this is a very crucial step. We notice that firstly x has degree at least k, y also has degree at least k. So this is at least k minus 1, this is at least k minus 1. We have one vertex here, one vertex here. So far everything is sum up together is at least a count of 2k, but we have exactly 2k vertices. So everything that I say at least is actually an equality. So this vertex set is exactly k minus 1 vertices, this vertex set is exactly k minus 1 vertices, and the whole, all the vertices represented here is actually the whole of G. So now let us consider G prime obtained by removing x, y, and all the vertices, all the edges incident to either of them. So all the white edges here. For G prime, n prime is equal to 2k minus 2, and the number of edges, because we can count how many edges has we removed. We remove k minus 1, and 1 edge here. So the number of edges is k squared minus 2k plus 2. And we check that this expression is exactly equal to n prime squared over 4 log plus 1. And so now we can apply the induction hypothesis to G prime as before. We get G prime has at least k minus 1 triangles. Okay, we seem to be one triangle short again for the original graph, but no worries, after we add back all of these edges to the original graph, we see that any edge in x or any edge in y will give the last triangle needed in G, and there will definitely be an edge in nx or an edge in ny because the bottom part here has triangles, so it cannot be bipartite. So there must be edges in nx and edges in my. So this gives at least k triangles, which contradicts the assumption we made over here. So the original assumption is wrong and there are at least k triangles. This concludes the proof of question 2. Hope you will enjoy this video. I think the whole phenomenon, even if the proof is quite complicated, the whole phenomenon of the supersaturation is something very fascinating, and indeed graph theory has many surprises. In the next video, I'll cover how we can use graph theory to prove a seemingly unrelated problem in arithmetic. So stay tuned and see you soon.